Hi guys, this is where we stopped in the last class. So let's proceed from here in the matrices. Engineering Mathematics 1. Okay. Using the row elementary operations, we can transform a given non-zero matrix to a simplified form called row echelon form. In a row echelon form, we may have rows, all of those whose entries we may have rows, all of whose entries are zero. Such rows are called zero rows. Okay. If a non-zero matrix is in row echelon form, then all the entries below the leading diagonal are zeros. Okay, that is we are actually converting it into upper triangular matrix. Okay, a similar way to propose for triangular form. There is two types of triangular form. One is upper triangular, second one is lower triangular. If a matrix is said to be upper triangular, you know the elements below the leading diagonal are zero. Okay, lower triangular, that also you know matrix is to be said to be lower triangular form if the elements above the main diagonal are zeros. Okay, right. So let's see some example for this. To make it into row echelon form, there are a series of operations he did. First you have to proceed with r3. Okay, r3 means row 3. Okay, r3 plus r1, if you add these two, this element becomes 0. That is the main idea. Okay, this is 0, this is 0, this will be 2 plus 2 4. Okay, what about this element? The r2 is 2 into r, 2 into r1, not r1. Okay, printing mistake. So minus 6 plus 6 0, 2 minus 2 0, right? 4 plus 4 8. Okay, so this is the required row echelon form. Okay, right. Reduce the matrix into row echelon form. The second example, you have to proceed with the main the diagonal element in the first row is 0. That's why they interchanged row 1 and row 2. Okay, now they proceeded with r3 as usual. R3 equal to r3 plus 4 r1 to make this element 0. So this is 0, this is right 2, because the other element here it is 0. What about here? 4 into 2 8, so 0 plus 8 is 8, 0 plus 4 into 5 20. Fine. Now r3 3r3 minus r2 to make this element 0. Okay, 3r3 means 6 minus 2r2 6. Okay, 6 minus 6 0. 24 minus 2 22. 60 minus 12 48. Fine. Is this the required row echelon form? See the dimensions of the matrix 4 by 4. Alright, 1 2 no, this is not 4 by 4, 3 by 4, right? 4 columns. This is not a square matrix. uh, Consider this one to be diagonal. Yes, this is the form. Okay, reduce the matrix into triangle matrix. Again you perform interchanging. Why you need to interchange r1 to r2? May not be required. Le- let's say they interchanged rows r1 and r2. That is fair enough. Okay, right. R2 is r2 minus 2 r1 to make this element 0. R3 is r3 minus 3 r1 to make this element 0. Okay, first see at r3 minus 1 plus 6 5 minus 2 minus 3 minus 5, right? R2 3 plus 4 7, 3 minus 2 1. Fine. Now this element you have to make it 0. So 7r3 minus 5r2. This must be multiplied with this must be multiplied with this. So this becomes 0. 7r3 minus 35 minus 5 minus 40. So this is the required triangular form. Now reduce this matrix into triangular form. Okay, right. R1 R2 are interchanged. Now like this. Why they are interchanged? Because one is good enough to have, right, in the first row, so that the reduction becomes easier. Okay, r2 minus 4r1, r3 minus 2r1, like that. Okay, so 1 5 7 13. What about this? 2 minus 2 0, 9 minus 10 minus 1, 1 minus 7, 1 minus 14 minus 13, 1 minus 26 minus 25. What about this? 4r1, right? So 3 minus 20 minus 17, 6 minus 6 minus 4 7 28. So minus 22, 25 minus 78, 13 4 42. Okay, so minus 27. Now R2 by R2 of by minus 1, R3 by minus 1, because all the elements are negative. Make them positive first. Then 17 R3 minus R2 to make this element 0. Right. So this is what you obtain. This is the required form, because this matrix has 3 rows and 4 columns. Okay. Fair enough. Let us do some exercises problems also. Reduce the following matrix into triangular form. 3 by 3 matrix. This is also 3 by 3. This is also 3 by 3. So out of 3, I will do 1, and this is 3 by 4. But the procedure is similar. Let me pick only one. Let me pick up this one, A1. Let me do it for A row echelon form. Okay. Right. Oh, what is the name of the matrix? There is no name. No name is required also. No problem. Let's write the matrix 3 by 3, right? Do we have 3 by 3 examples anywhere? Three by three. Okay, no, fair enough. Minus 2 2 minus 3. Where it went? Okay. Minus 2 2 minus 3. Okay. Minus 2 2 minus 3. 2 1 minus 6. 2 1 minus 6. Okay. Minus 1 minus 2 0. Minus 1 minus 2 0. Minus 1 minus 2 0. Bracket closed. Okay. Yes, this is the matrix, right? We have to reduce it into row echelon form. How to proceed? We will interchange, because first do R3 into, right, R3 of minus 1. I will write it here somewhere. Yes, here I will write R3 equal to R3. Yes, R3 into minus 1 into minus 1. I am negating R3, or I am multiplying R3 with minus 1. Fair enough? Yes, fair enough. Right. Okay. Then the resultant matrix will be same matrix. We can simply copy paste this matrix. Right. Only thing, the problem is this. Okay, we can adjust that, no problem. Okay, so this becomes plus 1, this becomes plus 2, that becomes 0. Okay, we just changed the um, sign, that is it. So now replace r3 with r1. Okay, interchanging, see the symbol of interchanging, yeah, r1, this r2. So r3, yes, r3 interchange with r1. Right, draw a line, yes, draw a line, no, put a line, then yes, put a line. Okay, that should have wait a minute, right, why arrows are this much lengthy? Okay, r3, interchange r3 with r3 with what, r1. Yes, interchange both. Okay, taking too much time. Okay, right. Okay, fair enough. Yeah, now interchange r3 with r1. The next step going to be right, paste, oh no, paste. Okay, 1 2 0 will go here, 1 2 0, minus 2, right, minus 2, 2 minus 3 will come here. Okay, fair enough, fair enough. Now there are two things we will do. R3 equal to R3 plus 2R1, right, R1. Similarly, we'll do one more operation here on R2 also. Okay, what is that operation? R2 equal to R2, sorry, R2 minus 2R1. Okay, because R2 has a positive element there, that is the reason. Okay, fair enough, right. Now what is the resultant? Go like this to find the resultant. Right, this is 1 2 0. Fair enough. This is 0. No, yes, r2 minus 2 r1, 2 minus 2 is 0. Okay, no problem, that is 0. 1 minus 4 minus 3 minus 3, right. The last element r2 minus 2 r1, 1 minus 4 minus 6, that is minus 6 only, no problem. R3 plus 2 r1 minus 2 plus 2, that is this is 0. Here 0. 2 minus 4, that means minus 1. Minus 1 being the next element. Yeah, right. Thereafter the third element will be minus 3. Yes, minus 3 minus 3 plus, that is anyway minus 3. Okay, 2 minus 4, yeah, minus 1 minus 3, right, minus 3. So bracket closed. Fair enough. Okay, now we need to do one more operation, because this element should be 0, right. So you have to make use of r2. Why? Because the first element is already 0. If you make use of r1, then you will end up getting one more element here which is non-zero. That's why make use of r2 here. Okay, that is 3 r3. R3 equal to, yeah, 3 times r3 minus 3 minus 3, so minus r2. This is sufficient, I guess. Yes, this is sufficient. So then copy this one, I can paste it here. Oh, right. Okay, copy this one. Yes, paste it here. Not visible, not visible, not visible. So we reach far ahead. Oh, fair enough. 1 to 0. So R3 only will change because of this operation. 3R3 minus R2. This becomes 0 as we anticipated. 3R3 means minus 3 minus 9. Okay, minus 9 plus 6 plus 3. Fair enough. So the elements below the main diagonal are all 0. So this is the required row echelon form. Okay, right. Fair enough. Okay. Transpose of matrix and its properties. The transpose of a matrix is obtained by interchanging the rows and columns of the matrix. A is denoted by A and its transpose is denoted by A transpose. Okay. A m cross n. Then A transpose will be Bij n cross m, where Aij equal to Bij equal to Aji. Right. For instance, this is the transpose. Okay. This row 1 root to 4 becomes the column in the transposed matrix. Okay. Results on the transpose. A transpose whole transpose equal to A. K transpose, where K is in a scalar, K into A transpose. A plus B whole transpose equal to A transpose plus B transpose AB whole transpose is nothing but B transpose into A transpose, reversal and transpose. Now let's see some example. AB whole transpose, B transpose, A transpose. We'll check these results whether they are correct or not. A into B is this. Okay. AB transpose is this. B transpose is this. A transpose is this. When you do B transpose into A transpose, you'll get the same result. Okay. So A plus B is this. A plus B transpose is this. Okay. A transpose plus B transpose is this. Okay. So A plus B whole transpose equal to A transpose plus B transpose. A minus B is this. A minus B transpose is this. Okay. A transpose minus B transpose is this. Both are equal. Okay. 3A is this. 3 into A transpose is this. 3A whole transpose is this. And nothing but 3 into A transpose. Similar problems are there. Okay. Very small problems. AB whole transpose not equal to A transpose B transpose, that also you can verify. Exercise is coming. I hope this exercise I need not to do anything except telling you to do on your own, because they're simple, such a simple and silly problems. Okay, if A is 3 by 4 matrix, B is a matrix such that A transpose B and BA transpose are defined. What is the order of the matrix B? Okay, A transpose B is defined. A transpose B is defined means A transpose having order 4 by 3. Let me write the order here, then you will get to know what I am talking about. Okay, I am just writing the order here. 4 cross 3 or otherwise 4 by 3 is the order of A transpose, right? So B must start with 3. The number of rows must be 3. B into A transpose is defined. So what is the order of A transpose? 4 cross 3. So A transpose order is 4 cross 3. So B must be having 3 rows, 4 columns. So B order will be 3 cross 4. 3 cross 4. Okay, so that is the answer. Okay, determinants, introduction to determinants, introduction of determinants, whatever it may be. The method of solving simultaneous linear equations was instrumental to the origin of the topic determinants. So the theory of determinants began with Leibniz, who solved the simultaneous linear equations. Definition of a determinant: the determinant is a scalar value that can be computed from elements of square matrix A denoted by det of A, or also with the symbol delta or det of A or det A. This is also the symbol for det. First order determinant: when A is the matrix of the order 1 by 1, then the determinant of A is defined as A. Second order determinant: always determinants are obtained for square matrices, that you have to remember in your mind. Okay. ABCD, what is the det of ABCD? 2 by 2 matrix AD minus BC. Okay. Third order determinant is somewhat tricky, somewhat involved. You have to go either choose a row or a column. You can take any row or any column to find the determinant. Okay, that you have to keep in mind. But it is always advisable to take only one row, while one row or one column, and stick to that particular column or particular row to get it familiar with. Okay, to acquaint with. Okay, so I'm taking this row, first row. Okay, 1 into then you have to uh, when you take 1, you shouldn't take this row or this column and this row, first row first column. Then the remaining 4 elements are there, right? Find the second order determinant here, that is minus 3 plus 0 or minus 0. Okay, then the second one will appear here. Okay, the sign will change, so this will be plus 1. Minus of minus 1 is plus 1. Again you have to omit the row which is involved and the column which is involved. Okay, Then find the second order determinant with the leftover elements, that is 2 3 2 0 1 3. So 6 minus 0. Okay, the third one will be positive only, so you have to omit this row, this column this time. So plus 2 into, find the determinant, second order determinant of this, minus 4 plus 1. Okay, that is how you have to find third order determinant. Okay, while making a generalization for any order determinant, you have to always if you take I as the row number, j as the column number, the sign, preceding sign here will be minus 1 whole power I plus j. This is first row first column, minus 1 square plus plus. This is first row second column, minus 1 whole cube. This is minus. Okay, so minus of this is plus. And what about this? Again first to third column, minus 1 whole power 1 plus 3 minus 1 whole power 4, that is plus. Okay, that is how you will find the sign. Okay, right. Properties of determinant. A and A transpose will be having equal value for the determinant. Okay, if you interchange any two rows or any two columns also, you will get the same determinant. Okay, this is the proof. Okay, anyhow you can prove, if any two rows or columns of a determinant are interchanged, then the value of determinant changes its sign. Its absolute value remains unaltered if you interchange any two rows or two columns. Okay, then the sign will change. Fair enough. If any two rows or column of a determinant are interchanged, then sign will change. If there are n interchanges of rows of matrix, then the resultant determinant will be minus 1 whole power n into det A. Okay, if any two rows or two columns of the matrix are identical, then the value of the determinant is straight away 0. This determinant you need not to compute, this is 0. Two rows are identical. Okay, if each element of a row is multiplied by a scalar k, then the value of the determinant is also multiplied by the same scalar k. Okay, right, like this, k1 kb1 kc1, first row is multiplied with a factor of k, determinant will also be multiplied by the factor of k. Fair enough. Property 5. If each element of a row of a determinant is expressed as sum of two or more terms, then the whole determinant can also be expressed as a sum of two or more determinants, like this. Okay. Determinant is unaltered when to each element of any row are added those of several other rows or columns multiplied respectively by constant factors, like this, a1 in plus p into a2 plus q into a3, b1 p into b2 q into b3, c1 p into c2 plus q into c3. Determinant will remain same. Fair enough. Fair enough. Yes, properties using problems using properties of determinants. Evaluate delta. C2 is C2 plus C3, elementary column operation here. This plus this, right? So A plus B plus C you can take into common. Then you got two similar columns, so determinant is 0. Similarly, you can prove this one to be 0. How? Alright, in this way, 2 A B B B C C C A plus B A B C B C, yeah, B C B C A B C A. Two columns are same. This is 0. A B C A B C. Two columns are same. This is also 0. Okay. X minus y minus z into z minus x. Here this guy is doing elementary row operations. R1 is R1 minus R2, x minus y, yz minus zx. R2 is R2 minus R3, so y minus z, zx minus xy. Okay, so these two are zeros. Take minus z common, x minus y, minus x common, y minus z. Okay, so now find the determinant. Since these two are 0, along this column you can find the determinant, right? Minus 1 whole power 1 plus 1, minus 1, this one minus 1 whole power 1 plus 3 plus 1, so positive only. So this row, this column will get eliminated. These four elements will be there. Expand along the first column. X minus y, first column, the common element that can be taken into out. Y minus z in the common element in the second row, that can be taken out. So y minus z, so 1 minus z, 1 minus x, right? X minus y, y minus z, z minus x, right? Product of determinants. While multiplying two matrices row by column rule, one alone can be followed. The process of interchanging the rows and columns will not affect the value of determinant. That is, we can also apply the following procedure for multiplication of two determinants: row by row multiplication rule, row by column multiplication rules, column by column multiplication rules, column by row multiplication rules. Okay. So if the same A and B are square matrices of the order n, then AB not equal to det of AB not equal to det A into det B. In matrices AB not equal to BA in general, so we can say AB det not equal to BA det. Let's see some worked out examples. Find the product of determinant by row column multiple. Okay. Okay, we'll first multiply the matrices and find the determinant. Okay. Yeah, det of AB equal to det A into det B. Det of AB equal to det of BA. Matrix multiplication, you won't get AB equal to BA, but in terms of det, they are same. Okay, right. AI, BA, CA are the cofactors of AI, BA, CA respectively from I 1 to 3 in cofactors. You might be knowing what is cofactor. A1 cofactor is erase this row, this column, whatever the remaining, find the det, that is the cofactor of A1, like that. So cofactor of A1 is capital A1. Okay, cofactor of A2 is capital A2, like that. Okay, first they are making the product. Okay, A1 A2, B1 B2, C1 C2, A1 A3, B1 B3, C1 C3. So these will become 0. Mod that A is this, that A square, that A cube. Okay, so this is that A square. Verify that data of a b equal to data a into data b. If a is this, b is this. Yeah, you can verify that, no problem. That's a big issue. A is this, b is this. Find the product of determinants by row multiplication. Okay, that you can do. Find that ab, that also you can do. So that z square is this z square equal to that, and that into that c square plus b square. Yeah, that you can show. Not a very great problem. Application of matrices and determinants, chapter 1.2. Okay, fine, fair enough. We'll proceed from here in the next session. Okay, thank you. Nandri, vanakkam. Are you tired of dental problems? Then listen to this. Stop brushing your teeth using plastic brush and chemical paste. Use nature's gifted neem stick for brushing your teeth and stay healthy.